The first part was about the mean curvature flow. Now it's a generalization of the mean curvature flow, which is called Brakke flow, and it was done by Brakke. So, motivations, again, it's not the real motivation of Brakke, but let it be the motivation of the second part of the talk. You have cities A, B, and C, and you try to connect them with roads with the least length paths possible. And the same thing for the cities D, E, F, and G. So we're gonna answer the question, what is the configurations that it satisfies the least length possible? Okay, now we go back to the motivation of the work of Brakke. We know the mean curvature flow, we know its properties for curves, for manifolds with higher dimension. We know that it develops singularity, as we saw, as the example we just saw lately. Now, what is the context we should adopt to define a mean curvature flow past singularities? So what Brakke proposed is the context of, well, let's say, the framework of rectifiable variables. We're going to define what is a rectifiable variable. We start with the definition of a variable. A D variable is a measure in Rn times GDN. A Ryder measure, any Ryder measure is a D variable. What is GDN? GDN is the space of D planes in Rn. So we take Rn, we take the space of D planes of, we take the space of planes of dimension D in Rn. If you consider Rn times GDN and we consider any Ryder measure on it, it's a variable. Radon measures, for those who don't know, it's just measures that are finite on compact sets. That's it. Well, let's think of a nice measure on Rn times CDN. It's enough. So we define the mass of a variable because it's something we're going to use later on. So we take a variable, we consider, instead of testing the variable on phi, which has two variables, x and s in GDN, we just put the variable x. So in other ways, we are projecting the variable on the Rn component. We are neglecting the GDN component. We are neglecting the tangential component. We are considering only the Rn component. And this is what I'm saying. This is exactly what I'm saying. Or we can see it in a different way. If I project on Rn, this is what we call the mass. When I put two bars, this is what we call the mass. The mass of a set A in Rn, a Borel set, but just think of any set, take any set, take its measure. It's the measure of the set times the Grassmannian. The Grassmannian is GDN. Okay, so I take a variable, it's a measure on Rn times GDN, take its projection on Rn, we call it the mass. Okay, now we consider rectifiable sets. What is a rectifiable set? In the geometric measure theoretic setting, rectifiable sets may be another thing in another domain, but in the geometric measure theory setting, it's the following. So if I consider rectifiable sets of dimension 1, it's just the union of curves, of C2 curves. And I allow singularities, like here, here, and here, and here. So we have tangent plane here, have tangent plane here. We don't have tangent plane here at the singularity. At any singularity, don't have tangent plane. Have tangent plane everywhere except at the singularities. Also, for two-dimensional rectifiable sets, it's just the union of manifolds of dimension 2, union of surfaces. Also, pars from surfaces. We just put them together We create some singularities, but the singularities are negligible. So this is a rectifiable set. So to be rigorous, a rectifiable set is any Borel set which is included in a finite union of submanifold of a given dimension, a given fixed dimension. And also there is another beautiful definition of rectifiable set. We first define what is an approximate tangent plane in the measure setting. So how to define an approximate tangent plane? You take any measure, you zoom out at the measure by taking modifiers which are converging to a point. You zoom out at the point, and if when you zoom out, you converge in the measure sense to a D plane, to a plane of dimension D, you say that this plane is the tangent plane of the measure at this point. So if you have something smooth, you're gonna converge to the tangent plane in this that we know in the smooth case. If you are not smooth, sometimes you have tangent plane, but you are not smooth. And if at any point when you blow up in the measure sense, you converge to a tangent plane, this is a definition of a rectifiable set. And there is a beautiful theorem that says that if at any point you converge to a tangent plane, you are rectifiable. This is a definition. But if you, sorry, I mixed things. A definition of a rectifiable set is anything which is included in a union, a finite or infinite union of submanifolds of a given fixed dimension. Now, I just explained what is a tangent plane. A rectifiable set, is if I take something that has a tangent plane almost everywhere, it is rectifiable. So it is included in a union, finite or infinite union of submanifolds. Hope this is clear. So you can just keep this picture in head, and it's enough to continue the road. So how to define a rectifiable varifold? We know what is a rectifiable set. We now define a rectifiable varifold. So rectifiable varifold, we take a dimensional rectifiable set, a d-dimensional rectifiable set. We take a function theta, which is integrable, defined on this rectifiable set, and we multiply it by the Hausdorff measure restricted to the rectifiable set times delta Dirac measure over the tangent plane at this rectifiable set. So I take the Hausdorff measure of dimension D because my rectifiable set is of dimension D. So naturally, I give it. I can define on it a Hausdorff measure of dimension D, and I take the tangent plane at any point. I take the tensor product, and I multiply by a function theta. We will put theta equal 1 for the rest of the talk, and this gives a measure, a natural measure on our rectifiable sets, and we call them rectifiable variables. And these are the context of work of Brakke. The mass measure is just neglecting the tangential part. It gives us the mass measure. Okay. Now the push forward of a measure. If I take a submanifold and I consider as a diffeomorphism, and I move the submanifold by this diffeomorphism, and I test on a function by the area formula or the change of variable formula, I get this formula. Here's the Jacobian, but the Jacobian is restricted on the tangent plane because we are not considering a Jacobian of the whole space, but we are restricting it on the manifold. So that's why we have this thing. Okay, similarly for varifold, to push a varifold is not something which has a full measure on the whole space. It has a dimension that we assign it to it. If we assign a dimension D to a varifold, so when we push it by a C1 diffeomorphism, it's going to behave as a manifold of dimension d. And this gives this formula. So to a d varifold, the push forward applied to a function is given by this formula. I replace phi of fx by phi of fx, but I also take into account the Grassmannian part, the tangential part, and here I replace the tangential, the tangent space by something, a variable in the Grassmannian, and I integrate over the Grassmannian. So this is a variable of dimension d. If the variable is a rectifiable, so I remove the Grassmannian from here, I replace S here by the tangent space of the variable because it's rectifiable, and here also, so it becomes the same formula. And here I remove this S and I replace V by HD, and I multiply by the density function theta. Okay, so what we should keep in mind is that push forward of a varifold, actual varifold, is like the push forward of a manifold of the same dimension. Okay, now we define a mean curvature of a varifold. So we define this quantity. This quantity is the variation of the mass in the direction of x a vector field in Rn. So it's defined this way. We push the variable by identity plus tx, and we take the derivative at time t equals 0. The derivative, as we computed before, is just the integral of the divergence. Instead of having the divergence of x, we have a divergence over a tangent plane s, and we take an integral over s. Okay, so it's just a generalization of in the varifold case. If the varifold is a C2 submanifold, as we saw in the first part of the talk, the change of the area, which is defined like this, is expressed in this way. So this formula allows us to define a mean curvature for general variables. How to do this? We know that in the smooth case, in the C2 case, we have this formula. So if I take the radon measure, the radon derivative of this measure with respect to this one, I get h. So in general, I define h as the radon differentiation of delta V over the mass of V. And when h exists, when V is smooth, we have the real h. When V is not smooth, we have a general definition of h. So now we defined what is a mean curvature for variables. Now we see an approximation of mean curvature for variables. So I take a smooth modifier and I just convolve delta V and V, and we can represent them in this way. We just pass the derivative, like here, we just pass the derivative over the modifier, and here we pass the integral, which is on the modifier, and it gives this formula. Well, the formula is not really important for the rest. We just to notice that this formula has very good properties. Is that it has convergence property and stability property. If V is rectifiable, so we can define if you can define H, the mean curvature, then H epsilon converges. If you have two variables, V1 and V2, if they are close enough, then their respective mean curvature, approximate mean curvature vectors are close enough. Okay. So now we want to define a mean curvature flow for rectifiable variables. The trick of Brakke was to look for an integral counterpart of the mean curvature equation. So what he did, he found a counterpart of the mean curvature equation, and he defined his flow, and he did a parallel work of the mean curvature flow, but in an integral setting. He transferred everything which is a differentiation to an integral, because he knows that in rectifiable variables, we don't have as regularity as for C2 submanifolds. And here's what he got. if you take a mean curvature flow, you take these quantities, you test it on quantities, and you take the derivative, you get this formula. From like in a sketchy way, you're gonna differentiate phi with respect to t, you get this. You're gonna differentiate it with respect to y, you get this, the gradient, and you're gonna differentiate the change of volume, and you know that your submanifold is moving in the direction of h, and you get this thing. This is basically how to prove this. So now, what do we have? We have an equation which is satisfied by the mean curvature flow, which can be satisfied by another measure, because we don't have anything here that cannot be that does not have an analogous in the rectifiable setting. We have h, the h we just defined with is analogous. The tangent plane, the rectifiable varifolds has tangent planes. So this is a good definition of mean curvature flow for any rectifiable varifold. So we go on. The computation we just saw implies this definition, inspires this definition of Brakke. So what is a Brakke flow? A Brakke flow is a family Vt indexed with time that satisfies the next. Vt is rectifiable, and we have a bound on the mass. Vt has a generalized mean curvature. Okay, so the bound of the mass allows tells us that it's not going to explode, so everything is well defined. The fact that and also that the tangent plane exists, and also we admit that Vt has a mean curvature, so we can talk about this equation, and the rest is what you expected, is the Brakke inequality. Let's say first we start with a Brakke equality. A Brakke flow is something that satisfies a Brakke equality. So this is exactly the equation we saw before, but with an inequality. So now I will explain why we have an inequality. We have an inequality because as the things we are considering are not smooth, so in some cases we might need to lose mass, like in an instantly you might need to lose mass, so we will lose equality and we put just inequality. But it's still a solid definition. It has very, very interesting properties that we're gonna see. So examples of Brakke flows. As we just saw, we have inequality here. So if I start with any variable and I set Vt equals 0 for any t, this is a Brakke flow because it satisfies this trivially, satisfies this trivially, and it satisfies this trivially. So the trivial flow is a Brakke flow. And this is the, let's say, the bad things about, like let's say, the only bad thing about Brakke flow. Everything, the rest is like is an ingenious work, except this thing, which poses some problems. Okay, mean curvature flows. Mean curvature flows are Brakke flows because we define Brakke flows starting from mean curvature flows. We generalize mean curvature flows. So trivially, mean curvature flows are Brakke flows. Okay, here are some examples of Brakke flows that are not mean curvature flows. Here's one. We take an 8 in R2. Brakke flow of an 8 might be this one, or might be this one, or might be some others. Okay, what happens here is that Brakke, when he encounters singularity, he gonna start with something. He gonna let it move like mean curvature flow. When he encounters a singularity, he gonna desingularize it. So this you desingularize this way or this way, and then you let the rest move as a mean curvature flow. So you desingularize here and you let it move as a mean curvature flow. You desingularize here and you let it move as a mean curvature flow. Okay, we saw that this thing develop a singularity here. So what Brakke does is start with this thing, he let it develop a singularity, and he desingularizes it this way. So, okay, this is in R3. I don't have good drawing skills. This is an R3. This is an R3. Something like a sphere. Is also something like sphere. He's also. So we have a singularity. We desingularize, and we let it continue as a mean curvature flow. So this is the motion of a dumbbell by Brakke flow. Here's another example of the difference between Brakke flow and mean curvature flow. You take a triangle. The mean curvature of triangle does not exist because it's not C2. You take a square also for the same reason. It does not exist. So what Brakke does, he desingularizes it here at the corners and then let it flow by mean curvature flow. And this is a generalization of mean curvature flow for any rectifiable variable, and in particular for a triangle and for a square. Okay. So the construction of Brakke flow. So the construction is very, very complicated. I am gonna explain it like in a sketchy way. You start with this rectifiable variable. You take delta, a time step, and epsilon, approximation scale, and you define h epsilon, the approximate mean curvature. What do? You desingularize, and then you do a push forward by this math, by this map. Delta is the time step, and h epsilon is the approximate mean curvature flow. And you desingularize again if there is a singularity, and you do a push forward by this. It's like you are discretizing a Cauchy problem, for example. We need the velocity to be equal to h. We're gonna choose delta, a time step, and epsilon approximation scale. We're gonna iterate, and then let them go to 0. And this is what Brakke does. He's gonna iterate these two processes, and he obtained this flow, this approximate flow, and he proved this. When delta and epsilon goes to 0, the approximate flow converges to a Brakke flow. So the approximate flow converges to something which satisfies all these properties. So the proof is delicate. It uses like very deep, very deep theorems from geometric measure theory. When you start with something rectifiable, first you should know how to choose delta, how to choose epsilon, how to define irregularly the desingularization part, and we go to the limit, why you converge, why the limit is rectifiable, and why it satisfies the Brakke inequality. All the works are gathered in one book written by Brakke, which consists his thesis. So I'm gonna jump over the proof. I'm gonna go to the properties of a Brakke flow. So one of the properties of Brakke flow is the avoidance of spheres. You take spheres in Rn, they are not normal spheres, but you let them move with a law which is not exactly the law of motion of mean curvature flow, because sphere is of dimension n-1. You let it move with this law. You put d here. D is the dimension of the variables. Anyway, you let a sphere move in a certain manner, and you let the variable move by a Brakke flow. We have this avoidance principle. If your variable does not see the sphere at time 0, its evolution does not see the evolution of the sphere at any time. So what implies is that if the variable is inside, it's going to stay inside the sphere. If the variable is outside, it's going to stay outside the variable. Sorry, if the variable is inside of the sphere, its motion going to stay inside the motion of the sphere. If it's outside, its motion is going to stay outside the motion of the sphere. And this has a consequence, which is the next. You cannot have a static Brakke flow if it's because compact static. If it's compact, it cannot be static because you can put it in a big sphere and you let the sphere move, and at a certain time, the sphere gonna touch this flow. So how to say, this flow, but the flow is static, so you're gonna touch the initial variable, and this is contradiction because avoidance principle that says that if you don't see each other at time 0, you don't see each other anymore. And a consequence of this, this is a generalization of another property, which is the non-existence of compact minimal surfaces, minimal submanifolds. You cannot have a minimal submanifolds of compact supports. This is a generalization. So a minimal submanifold has mean curvature equal to 0. So its mean curvature flow is just static. So it's Brakke flow, and then it's a Brakke flow, and the Brakke flow are static. So you cannot have a submanifold, a minimal submanifold in Rn. Okay. We have another avoidance principle which is stronger than this one. It's proved by Ilmanen. So if you take two Brakke flows, if they do not see each other at time 0, they do not see each other anymore. But one important condition is that they are of codimension 1. They are, let's say, of dimension n-1. So we saw for mean curvature flow is if you start with two mean curvature flows of codimension 1, so hypersurface mean curvature flows of hypersurfaces, if they do not see each other at time 0, they do not see each other anymore. So Brakke translated the proof in an integral way, and he proved that if two Brakke flows they don't see each other at time 0, they do not see each other anymore. Okay. So this has consequences, very interesting consequences, because we all ask the question like, in which situation Brakke flow is trivial or not? I mean, in the people who work on mean curvature flow and Brakke flow, they ask the question, in which case it's trivial, in which case it's not trivial. So in this case, this one and this one and this one, all these four cases, the Brakke flow is trivial. The reason is that you can draw a closed curve around this this rectifiable set, and this closed curve you can let it converge to the rectifiable set, and you know that their respective flows they don't see each other, and also we saw that the mean curvature, the extinction time of the mean curvature of a curve is proportional to the area enclosed by the curve. When the curve converges to one of these rectifiable objects, its area gonna converge to 0, so its flow will disappear in a very short time, and you turn this short time to 0, so the flow of any of these objects will disappear. And another interpretation is because you have endpoints, and at the endpoints you have a singular mean curvature that is pointing inward, so it's gonna push, and its magnitude explodes when epsilon goes to 0. So it's gonna push this object and gonna push it to a point, and then it's gonna disappear. On the other side, if you have something like this, like a circle with some, let's say, tentacles, these small things coming from outside from the circle gonna disappear immediately, because they have to avoid the evolution of this red curve, and this red curve is gonna get closer and closer to these things, so it's gonna push them, they're gonna disappear, and you're gonna only have a circle. So you start with a circle with this stuff coming from it, instantly it's gonna become a circle and gonna continue evolving as a circle. So we understand that Brakke flow just removes singularities and let the rest evolve as a mean curvature flow. Okay, we have a very interesting theorem. It's exactly what I just said. Brakke flow is just a mean curvature flow, except at some set of finite times. So we have a mean curvature flow. So I go back to an interesting example. Here, you have a mean curvature flow, something singular at this time. Otherwise, you have something which is smooth. Here also, you have a singularity here, and the rest is smooth. And this was proved by Brakke and some others. Okay. Now we go back to the question we asked in the first slide. So now here we finished with the most important things about Brakke theory. Here now the answer to what we announced in the first slide. So here there is a difference, a slight difference, is that in Brakke flow, in the original construction, you do not fix a boundary. The evolution we're gonna see here, we're gonna fix some points and we're gonna let the rest evolve. So Brakke didn't consider this case, but some people who came after and studied his flow considered this new case, where you fix a boundary, you fix some point, and let the rest evolve by Brakke flow. Okay, so we start with a direct proof of the question. The question was, if you have two cities, A, B, and C, what is the way the costless, the less costing way to link these three cities? I mean, you link these three cities with the least length of roads possible. So there is a direct proof. You take this your length, you look for a point P that satisfies the minimum, you just take the gradient, and as this functional LP is very nice, it's convex actually, the gradient is equal 0 only at one point. So you just compute the gradient. The gradient is equal 0 if and only if you have this equation. Okay. So you have 3 points, 3 vectors of unit length. They're some equal to 0. So obviously these 3 vectors satisfy the following. The angle between any of these 2 vectors is equal 2 pi over 3, 120 degrees. And we call this point Fermat point. And this point was proved, I mean, this result was proved way before, not using a flow, not using mean curvature flow, but proved in a direct way. And we know how to construct it. We constructed in a following way for those who are familiar with some planar geometry. We add some triangles and we draw some lines and we can construct a Fermat point. And this satisfies the minimizer. So in our context, how do we get this Fermat point? We're not going to get it in a direct way, but we're going to get it in a continuous way. We start with a random point, we minimize the length, and this is what a mean curvature does and a Brakke flow does, to get a minimum at the end. So the context is we fix A, B, and C. We put our point P somewhere, and we compute the mean curvature flow, and we do some Brakke tricks, and we move this point till we get to a point P, a point F that satisfies this. And how are we sure that we're going to get to this? Is because when we compute the mean curvature at a point P, the mean curvature is going to be this. Why? Because the mean curvature is what we get when we differentiate the area. And the area here is the length, the sum of lengths. And we saw that the differential of the length, or let's say the gradient, is equal to this quantity. Sorry. So when we take the minus, so we take minus the gradients because we want to decrease our length, we're gonna get the mean curvature. And if you let it flow by fixing A, B, and C, the flow gonna converge to this configuration, and we're gonna get our Fermat points, but in a continuous way, not in a direct way. Okay, we have a general. So now we answer the other question: how to link 4 cities. We have a general theorem that gives a characterization of any good configuration, a configuration with minimal length. If you take points in R2, A1 till AM, and we look for a minimal configuration, a minimal configuration satisfies the following. Only segments are allowed. You don't have any curve, only segments. And two different segments can intersect only at a perfect triple point, at a point where the angle is 120 20 degrees in any direction. And you cannot have like two different segments intersecting at a, you cannot have two different segments intersecting with each other without a third one. Okay. Here's an example of a minimal configuration. So you start with, we have, I don't remember the names of cities. It's like D, E, F, G, I guess, D, E, F, G, and you look for a configuration that minimizes the length. You get this configuration or this configuration. So I show this to show that there is not, we don't have a uniqueness. We don't have a uniqueness. So here at this point, you have 120, 120, 120, and same with here, just by symmetry. Okay. So the proof of the theorem. The theorem is in two parts. We only have segments, and at each intersection, we have an angle 120, 120, 120, that we called a perfect triple point. Okay, so let's say we have something like this, like two segments intersecting in this way. Well, the fact that we have two segments is we know that the segment is the fastest way that linking two points. Now, why we have only triple points with triple perfect points is because of this. We take this configuration. You know that this red configuration is better. It might not be the best, but at least this one is better. So if you see a point like this, you're gonna duplicate it into points, and you're gonna replace this configuration by this red configuration, which has a length minimal than the starting configuration. And the same, if you have like a lot of segments intersecting into points, and not only three, you're gonna do the same process, and you're gonna say you're gonna duplicate the points into 2 points and move them apart, and you have something with minimal length. And once you have this, you're gonna use the process, but by the Fermat point, or by the process of decreasing the length, that the best triple point is the point where the angles are 120 from each side. Okay, here are some examples. You start with this configuration, you apply the Brakke flow, or you minimize the length. You get this and this and that. From this configuration, you get this. From this configuration, you get that. And here are some perfect configurations. Okay, I'm gonna show at least one simulation. I have a video of that. Okay. I don't know which channels. Okay. So here's an evolution. We start with, okay, I'm gonna play it again. Start with this, and you get the perfect configuration. And here we have you have angles. The angles are 120, 120, 120 everywhere. Okay, I'm gonna go back to the presentation. Gonna make it bigger. Okay, so as for any problem that involves curvatures, Carl Friedrich Gauss tried to prove this problem, tried to find the solution to this problem, and by the time between these four German cities, Hamburg, Bremen, Hanover, and Brunswick, there was no railway connections. So Gauss worked on this problem, and he proposed a minimal configuration that links these four German cities. And he exchanged with some mathematicians and scientists, but at the end, I don't think he published his work. But anyway, he found the same configurations as he found the triple points with good angles. Well, one of the things why we don't really apply this in real world, because sometimes you have geographical constraints, and sometimes we have some cities which are more important than others. So in real life, you don't really apply this minimal configurations, but we add some weights. For example, like here we have, let's say Hamburg and Hanover are more important than Bremen and Braunschweig. So we would like to get a straight line between Hamburg and Hanover, and we try to link Braunschweig and Bremen in the middle because we want to get straight from Hanover to Hamburg. I'm just assuming that Hamburg and Hanover are more important than Bremen and Braunschweig, but I'm not sure. Just to say that in real life it doesn't work in this way. So do I have a simulation to show? Yeah, that's all for this. That's all for this part. So now, can we go beyond rectifiable variables? Can we go beyond rectifiable variables? This is the question that leads my supervisor to the work of my thesis that I'm gonna present in this short time I have. I don't know how many time I have actually. I don't know how much time I have to present the rest.
Well, I think yeah, not too much, but